I'm Dr. Günhan. I'm the Director of Construction Management Programs at Penn State University, College of Architecture and Environmental Design. Today, I'm very honored to introduce our speaker, Dr. Sez Atamturktur Russcher. She is the Harry and Arlene Schell Professor and Department Head of Architectural Engineering in the College of Engineering at the Pennsylvania State University. She conducts research in the area of uncertainty quantification and validation of predictive models of engineering systems. Her work has been supported by numerous federal agencies and documented in over 100 publications. Prior to joining Penn State, she served at Clemson University as Associate Vice President for Research and Distinguished Professor and founded the Office of Research Development. Previously, Dr. Atamturktur was at Los Alamos National Laboratory as an LTV technical staff member. The title of her speech today is The Future of Architectural Engineering Research and Education, Experiences from the Department of Architectural Engineering at Penn State University. I'm very excited to hear and be present in her presentation. Architectural engineering is an allied field of construction management. So we would like to we will be very happy and pleased to be informed about the recent developments and cutting edge research conducted at Penn State. Welcome, Dr. Russcher.
Thank you so much, Suvat. I appreciate the invitation and thank you everyone for joining us today. I divided this presentation into three rough sections. I'm going to start with explaining who I am and what I do, a little bit of my background and how I ended up being the head of the department at Penn State Architectural Engineering. And next will be about a little bit about my research. I only have 8 slides to talk about how uncertainty quantification and model calibration validation applies to a variety of engineering fields. And I'm hoping some of those ideas will be relevant and interesting for you as well. And I conclude the presentation with my department and an overview of our curriculum and our priorities, as well as a brief summary of some of the research projects my faculty are working on. All right, so I'm Sez. I go by Dr. Sez or just Sez, like he says, she says, or Simon says. I graduated from Penn State. I obtained my master's from Architectural Engineering Department and my PhD from Civil Engineering. And shortly after that, I actually had a little stint at Los Alamos National Laboratory because Los Alamos funded my doctoral work when I was at Penn State. I started at Clemson University afterwards, and I worked on what we call MVUQ, model validation and uncertainty quantification. In 3 years, I became an associate professor. I got promoted to associate professorship. In 6, I became a full professor. And in 5, I was an endowed professor. And since then, I have been either a distinguished professor or an endowed professor. Before leaving Clemson University, I was Associate Vice President for Research, as Suvat mentioned, and I'm going to go over some of the responsibilities I had and experiences I gained that prepared me to be a department head. And finally, I'm currently the head of the department, and architectural engineering at Penn State is the longest existing accredited program in the country. We are the largest in terms of our student body, in terms of number of our faculty members and the research we do. So my background, I want to give a little bit of an overview about what I do and why my work is so interdisciplinary. My background was a PhD from civil engineering and with a focus on structural engineering, yet it was funded through Los Alamos National Laboratory's X division, which had a strict focus on stewarding nuclear stockpile of the United States. And in that, as I was working at Los Alamos, I interacted with mechanical engineers, aerospace engineers. In fact, my immediate supervisor was an aerospace engineer, and of course, nuclear engineers and statisticians. And when I joined Clemson, I joined through the civil engineering department, and I was also, portion of my salary came from 50-50 from mechanical engineering. I was also affiliated with industrial and environmental engineering departments. The reason I'm giving this overview of how broad my training and my preparation is because my work is very generally applicable. I develop algorithms that anyone can actually take and deploy in their fields. As long as you know the inputs and outputs, And as long as you have a model that can predict those outputs for given inputs, and you have some experimental observations from the field, my algorithms will allow you to bring those models and model predictions and experimental observations together, and with the intention to improve those models and lead to better decision making. So at Penn State, department heads are considered chief academic officers because Penn State is so large. We're very decentralized. So in a way, department heads act like mini deans. We are responsible, for example, I am responsible for every human resource aspect as well as budget, maintaining our facilities. Obviously, I do extensive fundraising, and I'm responsible for the communication efforts of our department. And I hire faculty. So at Penn State, department heads have tremendous say in fact, they are the decision makers when it comes to hiring faculty members. And since joining Penn State, I hired faculty with really different backgrounds. So that's one of the things that make my department so unique, that we bring engineers from various engineering disciplines under one umbrella to solve really focused problems as applied to building industry. So some of the faculty I hired had acoustics backgrounds, some were electrical engineering PhDs, some had mechanical engineering PhDs, yet we are all in this one department and collectively working to make buildings and built environment better. Since I joined Penn State, we had tremendous progresses. Our enrollments have been skyrocketing. We went from about 290 students in the program to well over 500. Our PhD student numbers went from 20 to so right now we're at 98 PhD students. So we had a lot of progress, a lot of activity. So it's been a really fun time with tremendous forward momentum. And we are moving into a new building. So the building you see on the right side, the 5th floor and the 4th floor are ours. My department will move in by the end of December 2020. So by the end of 2023, so in December we will be moving. They're very excited about that. Obviously, as we were designing this building, the planning for this building started when I became a department head. I basically took the laboratory facilities we had in our current building and just scratched them and said, let's start anew. Let's think about the future of architectural engineering research. So we developed a whole lot of new ideas about how research will change and advance in our field, and designed laboratories that will distinguish our faculty moving forward. I also would like to point out that I serve on the board. I think it's relevant for this community. I am a board member, one of the board of directors for the National Institute for Building Science. If you're not familiar with NIBS, please do Google it. It is a congressionally mandated entity predominantly funded by federal contracts, reports directly to the President of the United States, and established in 1947 with the mission and vision of bringing industry, academia, and government together to improve the built environment. So many of the students and faculty in this audience will probably appreciate being part of that NIBS community. My department also has a very strong established partnership with United Nations, and through our United Nations connections, we received support from the World Bank, where students from developing countries can secure funding through the World Bank to come and obtain their master's degrees with us. Before joining Penn State, I was at Clemson University. In fact, Penn State pursued me for 2 years. My responsibility was furthering the research portfolio of the entire institution. I essentially had 4 broad areas of responsibility, and the 5th one was just added as I was leaving the institution. I oversaw the limited submission down select process, meaning that anytime we had to determine who is going to represent Clemson University, my office, for proposal submissions, let's say MERSECs or SDCs, my office made it down select, formed the teams, provided seat support. I developed year-long faculty development programs for junior faculty to get them acclimated in research and get them familiar with the federal and also industry and philanthropic research programs out there that can support and enable our faculty's research. And I was responsible for strategically positioning the institution for large-scale initiatives. So anything like $100 million research investment will be something we will be working a few years ahead of time, making the right connections with government relations and industry partnerships and investment from the university to enable those kind of successful projects. At the time I served 1,400 faculty members in 7 different colleges, and it was a really eye-opening experience, and I believe a very valuable training experience before I became a department head. I mentioned the 5th responsibility that's not listed on this page, and that was cluster hiring. The provost, Bob Jones at Clemson University, asked me to look at the university's research portfolio and faculty capabilities to identify gaps and meaningful investments that we can make to connect different clusters of excellences within the university. So I actually looked at the institution with a really broad scope to understand what our distinguishing features were in not only our faculty expertise, but also our experimental facilities. I had many projects, and I led several large-scale initiatives during my time at Clemson and as well as Penn State. This is one example. I was the principal investigator of a national research traineeship project. In that project, I brought together faculty from a variety of different colleges that focused on infrastructure resilience. So again, this project might be of interest for this community here. What you see on this bottom left corner, that figure shows the interdependencies between different infrastructure systems for different spatial and temporal scales. And in that figure, my job was to be an arrow. I helped couple faculty members, different faculty members of different research teams, computer models, and all while propagating uncertainties and errors and quantifying the risks associated with using these models for decision making. And the beauty of this project was, because everything was coupled with each other, we had to make sure each model was reusable and individually validated, and they really played to the strengths of my research program. So that essentially put me and my students at the heart of this initiative, and me being a PI was a really good fit. Okay, so I'm gonna just talk very briefly about my own research because I think it's very interesting. All right, so I work in the area of simulations and theory, first principle physics and simulations and experimental observations. So if you look at like way back before the major advancements we made in computing tools, the historic scientific inquiry was very reductionist, and we will collect a large number of experiments and then try to fit some sort of a relationship to retroactively understand what those experiments were telling us. They're very empirically driven. And since 1960s and beyond, we focused a lot of emphasis on simulation-based methods, where simulations are developed based on first principle physics understandings. And a very small number of experiments are conducted to be able to validate these simulation models. And that actually how my work at Los Alamos originated in the second simulation paradigm. The reason I was hired at Los Alamos was because Los Alamos is the stewards of nuclear stockpile, yet they cannot do experiments. Either they are environmentally risky, they might be unhealthy or create a health risk for the population, or some of these experiments take too long, or they're very expensive. For one reason or the other, experiments are very rare, and we never have the whole system experiments. We have only benign experiments of maybe some components in controlled settings. So that's the environment I was in. Models were physics-based, high fidelity, and the goal of the modeling was to make simulations as faithful as possible, as informed by first principle physics as possible, such that our reliance on experiments is as minimal as possible, because experiments are so expensive. So essentially, I was in this really data poor environment majority of my career. And with advancements in data revolution, and now we have so much more data, not only just veracity, but volume, variety of data we have. My work over the last several years started to change a little bit and take advantage of large amount of data with very high fidelity physics-based models, and how to integrate them such that we actually can do a bit more than calibrating uncertain parameters, dive deeper into the first principle physics. Can we empirically infer what those first principle physics are? So it's a tighter marriage of experiments and simulations, and a little deeper dive into to the first principle foundations of simulation models. So I'm going to give this, I prepared this really cartoonish simulation. I hope you will bear with me because this is really exciting in my opinion. Okay, so now let's look at the top figure over there. The black squares are my experiments, and they have certain experimental uncertainty, right? And the solid red line is my simulation model at its nominal setting. So let's assume that my simulation model has one uncertain parameter, let's say theta, and X here determines the control parameters within which the system should operate. A really good example, let's say I'm an aerospace engineer and I'm designing this airplane wing, and my control settings, X could be, for example, the wind speed, or could be the angle of attack of the wind, whereas my theta uncertain parameters will be the composite material properties of the wing. So the key here is I know X, but I don't know theta. And theta is uncertain, hard to know variable, yet X is a domain within which my engineering system should function. When I conduct experiments, I can control X. I have an idea about what X values will be when I try to compare my model simulations with experiments. That's why if you look at the black squares, they have each of them have a corresponding X value because I conducted those experiments. I know what control settings they correspond to. But again, I don't know what my theta is. I have an idea. I can say my theta is anywhere from -1 to 1. It's within that range in this cartoonish example. And a logical next step might be to say, I'm going to sample this theta to see if any one of those theta values, given the theta's uncertainty, will better fit the experimental observation. So what you see over here is an ensemble of model realizations, multiple solid red lines. And as you notice, none of them actually completely go through all of the experimental data points. And the reason for this is because I faked it. What I did was I used a different function that also had a sinusoidal term, one extra term when I was generating my experimental observations, but I took that term out and made my computer model incomplete or incorrect or a simplified version of reality, as a result of which my computer model will never completely match the experiments. So I can calibrate my theta all I want, but there is an inherent incompleteness, inherent bias in my model simulations just because that sinusoidal term is missing. So that sinusoidal term's effect is shown at the bottom of the third figure as dotted line, and it says discrepancy. So the key here is, if I can figure out what that discrepancy is, then I can actually tell how wrong my model is and possibly correct that model and get the truth. So that's the utopic or the intentions that this type of approach has. I have a little bit of equations here. I'm gonna skip them, but if anybody's interested, please let me know and we'll come back and go over those equations and what they mean. But one thing to pay attention is the last one over here, right? Y is the experiments, eta is my model simulations, X is my control settings, let's say temperature, wind speed, theta, let's say my material properties are uncertain parameters, and that discrepancy term is my model's bias, and then the last term over here is my experimental uncertainty. So try to remember this, because the key here in my work is we determine theta and the discrepancy simultaneously. Okay, because if we don't do it simultaneously, my theta calibration parameters will end up masking some of that model bias. So a very popular approach for handling this problem is using Bayesian statistics and using very informative prior distributions on the theta. So for example, remember in the previous slide, I said my theta is anywhere from -1 to 1. So think about it, if it's like still Young's modulus or infiltration parameter for airflow in a building. So you have some idea, you may not know the exact value, but you have an idea about what the range is. That's essentially what we use for our priors. And then for that model error discrepancy, a common application is to use a Gaussian process model, and that's a non-parametric family of emulators that I'm just going to call it a fancy polynomial that fits using the experimental data to tell us what the model's error is. So if you look at the top figure over here, you see the prior distribution that's uniform between a minimum and a maximum. So -1 to 1 or 10 to 20. those maximums and minimums come from your subject matter expertise. And then when you sample this, you obtain model realizations, and those are these green solid lines. And once again, I have these black squares that show you different experiments that are conducted. So in the next figure, I'm going to calibrate this prior and obtain a posterior distribution. As you see, the posterior distribution is much better defined, meaning that I learned from experimental data what the likely values of this parameter is, as a result of which my model's predictions are much narrower, much better defined. So you see those blue solid lines, they are much narrower dispersion than the green ones. But the really interesting aspect of this work is, as I was doing that, I also obtained my model discrepancy, which is the one right at the bottom, the red lines that show you that my model is under predicting certain settings and over predicting at others. And I can use that information for a whole sort of interesting things. For example, I can tell where to conduct the next experiments. I can look at where the model developer should focus their attention. Maybe there's certain physics principles that are really active in the low temperature ranges and they should be focusing. So I can give that kind of insight and help decision makers better allocate their limited funding, limited money to either experimentation or model development. So that was a really critical decision-making framework that we were able to develop using this approach when I was at Los Alamos. Okay, so now this is going to go into this tighter marriage that I mentioned, like a better tight relationship or more tight relationship between experiments and simulations. So here is one key aspect of the previous approach that I presented to you. It assumes the posterior distribution, that blue probability distribution, to be constant, fixed for all values of x. So essentially, we obtain one probability distribution for the entire domain of applicability. All values of x, posterior stays the same. But then we realize it doesn't have to be that way, right? There could be situations where model discrepancy originates because certain relationships between parameters are not accounted for. So that could mean that there exists a data parameter. It's not constant, but it's actually functional. It varies as a function of x. So what it does is it recognizes the fact that my model is incomplete. Remember that sinusoidal term that I was missing? So it's essentially, I'm trying to figure that out. I'm trying to figure out what term is this numerical model missing? Can I learn it from the experimental data? So here, my functional data is function of x. And what that means is I can actually learn more from available data if I take this approach. So I'll give you an example. This is a code that we developed, and I didn't develop it, material scientists developed at Los Alamos National Laboratory. It's called viscoplastic self-consistent, and it's designed for metal, polycrystal metals. It's specific applications to rare earth materials like zirconium. And this model is really effective in estimating the stress strain diagrams of zirconium, for example, at really high temperature, high pressure settings. So like in nuclear reactor environments, for example. So what you see over here is 4 different experiments conducted at 4 different temperature settings. However, you will notice that even though the response stress strain curve is changing depending on the temperature, VPSC code did not have temperature as a input. So you had no way to incorporate the effects of temperature when you were running the VPSC code and obtaining your prediction. So you essentially will obtain one value that will be a straight line. I'm sorry, that will be a constant for all temperature values, regardless of what the temperature setting was. And the question we asked ourselves, can we figure out what relationships are changing, or what relationships, or what terms in the model are dependent on temperature that needs to be taken into account? So when we do that, oh, I should mention, the fact that VPSC does not take into account temperature is what we call a model misspecification. In other words, this model is incomplete, right? It's missing a really key feature that needs to be accounted for. So if you remember that earlier equation, we had eta x theta. Now I have eta x theta x. So now my theta is a function of the control parameters. When we do this, the whole formulation of our Gaussian processes and the inverse analysis through macro chain Monte Carlo needs to be completely re-envisioned. But the risk is, though, even though this approach allows us to learn more from the data, the risk is it can make the problem unidentifiable. And what that means is 2 + 3 is 5, 3 + 2 is 5. I can't quite tell which one is which, right? I need sufficient amount of data, but I also need to leverage every expert judgment, subject matter expert information I possibly can. So for example, we incorporated things like, oh, the Gaussian process must be monotonic because as stress goes up, strain goes up. That's common sense. We impose things like at the extremes, the behavior should be asymptotic. So we put certain restrictions on the derivatives of the Gaussian process. So we incorporated a large set of limitations and constraints to be able to reduce our demand on experiments and still get an identifiable solution. We had a number of journal publications on this. If anybody is interested, I will be so happy to tell you more about it. Here is a zirconium bar that was bent, and we did a dot point experiment on it, and we see the corresponding finite element model. If you look at the bottom here, you see this really simple equation. I mean, it's one of the many terms in it, but that's really the key one that we were focusing on in this VPSC code. This particular step in the process has two parameters, Ng, which was constant for all values of temperature, and the one in the bottom is our shear threshold, and that was variable. And we were able to infer what that variability, what that relationship was between the shear threshold and temperature. And once we incorporated that into VPSC we didn't change the VPSC code at all. We incorporated temperature through the shear stress values. We were able to better match the experiment. So now that we have a way to incorporate temperature effects into VPSC code without necessarily changing the executive code itself, but also now the code developers, material scientists who dedicated their entire lives developing this VPSC code know that that relationship between shear stress threshold and temperature is there, and now they're going to dive more deeply into it and incorporate that into the code in future years. All right, so I'm just gonna skip these slides a little bit, but my algorithms were also used to guide decision making in terms of how to use your precious funds for experiments. So if you give me a first batch of experiments, I can tell you where the next batch should be, which is the red circles. And then if you give me the red circles, I can tell you that the next batch should be green diamonds, to such that your model converges to the best outcome with the least amount of experiments, because remember, experiments are expensive. At least that's the environment that I was in. We also looked at coupled formulations, multi-scale problems, multi-physics problems, where the uncertainties and errors propagated between different legacy codes, and we were able to mitigate the uncertainties in each of the scales or physics models. These are probably going to be a whole hour-long presentation themselves. I'm going to skip, but if you're interested to learn more, please ask me questions. All right, now, finally, enough about me. Let's talk about what architectural engineers do and how my work, I'm going to try to touch on how my work applies into the field of buildings as I talk about some of the work that we do and my faculty work on. Okay, so architectural engineering at Penn State was established in 1910 with the objective of integrating this artistic arts and then engineering, like mechanistic principles. And we are, as I mentioned earlier, we are the longest lasting accredited architectural engineering department in the country. And so if you look at the description here, this is our plaque right in front of my office. It says the aesthetics, and then construction, and then architecture, and the useful arts. That's where the engineering comes in. So this is a really important field just because we spend a lot of our times indoors. So my department focuses on making buildings cheaper, healthier, more efficient, more robust, secure. Every aspect that you would like, every positive adjective that you would like to add to a building, that's what we work on. And we believe our work is so important because people spend so much time indoors, and we work on making that environment better for everybody. So the term, you must have heard from National Science Foundation or the federal government, there is this big push towards convergent research, bridging disciplinary boundaries or silos and bringing people from different backgrounds together to collaborate. And I prepared this presentation, this particular slide, when I was interviewing for the job that I currently have. And my pitch was, Penn State Architectural Engineering has been exercising convergent education since 1960s, before it was a popular topic, because we really do bring a variety of different engineering disciplines under one umbrella. Our department is a 5-year curriculum, and we have 4 different option areas. So it's 162 credit hours curriculum, so it's pretty hefty. So first year, every student is in the general engineering program. In the second year, they get to take some basic introductory courses, and they also take architectural design studios. And this is really important because our architecture courses are taught by architecture faculty from the College of Arts. So it creates a bit of a tension, right? Engineers trying to work with College of Arts faculty, and we have to figure it out. Sometimes our students don't like it, and sometimes they love it, and we had to collaboratively develop and refine the curriculum over the years. But the fact that architecture faculty teach our students is, I believe, a distinguishing aspect of our department, because my students take 4 architectural design studios. We just changed the curriculum, made the 4th one elective, but they take 3 to 4 architectural design courses, about half of what architects, close to half of what architects take. And when they graduate, they understand the painful process of designing a building as by an architect. They can appreciate it. They can have that language. They can communicate. We also pay a lot of attention to our students' drafting skills. Like, take a piece of paper and sketch your idea, sketch how you want the design to shape, because we want our engineers, architectural engineers, to be in the room, change agents, and making a positive impact on that architectural design, not just taking whatever the architect designed and then trying to figure it out afterwards. We want our engineers in the room as the design is taking place. So that's what we take credit for, or that's our claim to fame. All right, in the 3rd year, our students they start to get introduced to different option areas. So we have 5 introductory courses. We cover structural, mechanical, construction, lighting, electrical, and acoustics. Even though acoustics is not acknowledged as a specialty area its own, it probably will be in the future because that's a really popular area. And mechanical and acoustics kind of go hand in hand. After students finish their 3rd year, in the 4th year, they get to choose a specific topic or this option, and then they start to take a number of elective courses, and that's the 2nd time they're taking 2 semesters of architecture. So they did it in the 2nd year, they're going to do it in the 4th year, and our 5th year is our capstone design studio, where they essentially design a whole building in teams, or they can design a whole building by themselves. All right. Okay, so we covered that. So we focus on the indoor environment I mentioned, making individuals, building occupants more productive and healthier. We focused on energy. My faculty, in our education and research, we focus on making buildings energy efficient. And then we pay great amount of attention to retrofit strategies, because the existing buildings are great, and my students know how to design new buildings, but we also want them to be able to go into an existing building, read the building codes, do some forensic analysis, and develop repair and retrofit strategies. And of course, affordability and accessibility is a high priority. This year, we also started engineering with societal impact focus. Our faculty came up with the idea. Now our capstone projects is not just designing a building, but designing a building with the information provided about the community. So let's say you're designing a factory and it's next to a low-income community. How would you take that into account, and what kind of decisions would you make? So the social science aspects are starting to get a bit more attention in our engineering curriculum as well, which I believe is a positive thing that we're doing. Oh, we have the world's largest architectural engineering career fair. Every year I have about 250 companies signing up to participate in our career fair. I can only admit about 140 to 150 of them. This is Bryce Jordan Center. We fill it all up. My students have 100%. These numbers are a little old. This year we were able to fit about 150, and we turned away about 100 companies. All right, I'm just going to skip those numbers because they don't quite apply. Those numbers have increased dramatically. our students, I should mention, we have 100% job placement before graduation. So by about November, about 85% of my students that are going to graduate in May are gone. And by August, about 50% of them are gone, just because they accept the offers in their internship before coming to me for their 5th year. My students are also very active in a variety of different design competitions. So Architectural Engineering Institute has a design competition. In 2019, they got every first place, and in 2019, they got 4 out of 5. So every year we end up winning. Pretty much every competition they participate, my students are in the 1st or the 2nd place in the nation. I'm just so proud of that. We have embedded study abroad programs in the department. So we have one in China, we have one in Belgium. I'm showing here the one in Honduras. That was more developing countries and solar panel installation focused. And we have one in Italy, Rome. And they are what I mean by embedded is our faculty teach these courses. So, and they're part of architectural engineering credits, like credits in the major. It's not like a university organized study abroad, and Penn State has plenty of those. But we design, in our department, we design our own study abroad programs and take our students abroad. In our graduate degree, we have a Master's of Architectural Engineering degree. So that's the Master of Engineering in Architectural Engineering. It's only like you take courses, it's 30 credits, you take 10 courses and you obtain a degree from us. It literally puts you at the heart of the building and construction industry. I mentioned 100% job placement for our undergrads, but we also have 100% job placement for our graduate students, both Masters and PhD. So faculty members in our department focus on various aspects. Performance is a huge aspect, anywhere from the new materials to modeling and simulation. The top 2 items that you see under the potential innovations, that's where my research fits in. I work on making building energy models more reliable and quantifying the uncertainties in building energy models, for example. I have a number of faculty that focus on predictive control. We have faculty members that put sensors on human beings, occupants, and integrate it with the building control systems. There is a strong construction emphasis in our department as well. We have a large number of faculty that focus on robots, robot and worker interaction or collaboration and cooperation. Building automation and robotics is a huge focus right now for us. We have a robotics laboratory as well as a whole digital twin laboratory that where the BIM models you guide robots about what to do. In addition to changing the way buildings are constructed, we're also changing the way buildings are designed. So I'm a structural engineer, right? The connections for a steel building, for example, were designed with the human workers in mind. If a robot will be building the building, I can actually, as a structural designer, change the connection. So there is this structural systems and construction manager integration and collaboration going on as well. Safety, we have one faculty member who received 4 projects this past month on construction safety related aspects, a huge area as well. And then I have a large number of faculty members that are focused on sensors and controls in various aspects of the of buildings, anywhere from controls for energy efficiency to preventing active shooters or keeping an eye on the elderly. It's pretty broad. I'm keeping an eye on the time here. So this is Wang De Zhu. Wang De develops Modelica tools for building energy models. He's actually one of the most, his research group is like 16 PhD students or so. It's one of the most prominent groups in the nation when it comes to building energy models. You can see here the scales that he works on, anywhere from the individual building all the way scaled up to a community, to a neighborhood, and a state level simulations he can make. We have another faculty, Yuqing Hu. She comes almost from the other side. She focuses a lot more on the city level energy consumption and distribution of solar panels, and she has a construction management background from Georgia Tech, yet very strong energy focus. Alp Durmuş is a lighting faculty. He designs new lighting fixtures as well as new ways of measuring and quantifying lighting for lighting comfort. So for example, if there's glare on your computer screen, there's data that shows that the performance of the workers will be lower. When you think about corporate America, majority of a company's expenses are the human capital, salaries that you pay to your employees, right? And if your employees are not as productive, that has a huge impact on your bottom line. So those types of aspects of the light and light comfort and productivity, Alp studies them. He got a recent project looking at sport facilities and outdoor lighting and energy aspects as well as comfort. This is Julian Wang. He develops new materials for building envelopes, predominantly for the glazing materials. He tries to get the daylight in, all while keeping the solar radiation out in the summer and letting solar radiation in the winter. It's pretty interesting, pretty exciting work. Obviously, he does a lot of experimental work as well as simulations. And at this particular faculty is Greg Pavlak, and he's very focused on controls and coupling buildings to each other, as well as coupling buildings with the energy grid, and enabling the penetration of renewable energy. And so he develops these algorithms that can do transactional contracts. So for example, I have excess energy and I'm going to sell it to the grid, and how much should I charge? What is a fair rate? Or let's say Suat and I are neighbors, and Suat has excess electricity and he wants to sell it to me, but how much should I pay, or how much should he charge? So he develops these very quantitative, uncertainty aware mechanisms for optimizing system level performance, all while taking individual well-being and into account. All right, so that is pretty much it. I went through this pretty fast, and I hope this was exciting, and I'm hoping we have enough time for questions.
Thank you so much. I'm really impressed with the content you showed us today. It's great. I would like to start with my question here. So if your students, they choose structural specialization option, or let's say mechanical, are they on their way to become a structural engineer professional or professional engineering license?
Yeah.
Do they still take courses, additional courses from mechanical engineering or
No,
structural engineering? No? Okay.
It's all in us. So actually, I'm so glad you asked that, because increasing our students' FE exam take rate is one of my initiatives. My students have incredible success rate compared to national averages, 17% above national averages, anywhere from 11. So last year we were 17%, the year before we were 11% above national average. So when they take the test, they're passing it. They can take it for structural, they can take it for architectural engineering. So they get to choose. Some of them actually go after electrical, but the courses we cover are sufficient for them to take FE in their chosen option, just because they take a lot of electives. Once they choose an option, they take a lot of electives, a lot of core technical courses. And our entrance to major courses in the first year, remember I said in the first year our students are in general engineering, that is essentially the same curriculum for all engineering students at Penn State, and that covers the mechanics of materials, engineering economy, a lot of the stuff that is in a FE exam are covered in there. My problem is the take rate is low, and it's only like 35 to 40% of the students are taking it. So we have this big initiative to encourage our students to take the exam. We're doing review sessions. We're giving them even financial incentives. But yeah, they take it, and they have a great pass rate. They can take an AE or specialized options. However, they're less likely to take the FE exam than perhaps some other departments where it's like Nebraska's architectural engineering has a mandate. They have to take it. They don't have to pass it, but they have to take it before they graduate. And we don't have it in our department. And we've been debating, like, should we make it a requirement? Because I really would like us to get to 100%, at least to take. I mean, my students will pass. I want them all pass. But anyways, yeah, I hope I answered the question.
Yes. Thank you. And the second one is, I believe, what is the niche market for your students for employment? It's mostly design build. I'm thinking the best match, the best fit for your is not.
Yeah.
Okay.
No, all kinds. Yeah. So I mentioned we have 250 companies signing up every year to come to our career fair, and I turn away about 100 of them. And that's like the worst week of the year, because people are upset at me that they couldn't get into our career fair. And the companies, and it range from design firms to construction firms to design build firms to real estate development companies. They're hiring engineers, owners representatives, so major corporations that have a lot of real estate, government organizations, for example, want engineers representing them. So that's another area. I think that's pretty much it. Like for so the companies that have been admitted to participate in our career fair on our website, we update that information every year. So you can actually go and see if you print the 400 largest design and construction firms, they all attend our career fair.
Oh, great, great. So then how do you motivate your students to choose the best options available? I mean, what we had as an experience in our career fair last couple of weeks ago is that we had many companies. I think this is, we have a hot market. I mean, usually AEC industry is doing well anyway, but I think we wish that we had more students attending career fair. Well, how do you motivate your students participate career fair? Because I understand that they have many options.
Yeah, of course. So my biggest problem has been that a lot of so our career fair is in September. So beginning of fall semester. The problem we were having was a lot of my students were coming to 5th year already with an offer accepted. So when I first started as a department head, I had to do a lot of lobbying and telling students, don't accept your offers, because the data shows that the sooner they accept, the lower the salaries. If they wait a little bit, actually, it gets more competitive as students get snatched up. So that message started to be like students are negotiating better and standing up for themselves better, and they're not accepting the pressure from companies anymore. And we had a lot of how to negotiate type workshops. And we have a student organization in my department that actually coordinated and facilitated many of those workshops, and we sponsored it as a department. And my message was, if a company pressures you, that's not a good environment, right? Just ask them at least until October. So that was one good change. And the second one is that career fair is such an integral part of our culture that all the faculty in the department recognizes the career fair day. If a student has to take the day off, they're going to give them remedial material. Everybody's lenient and understanding. Some faculty members do give like extra points, like go talk to these companies and ask them these questions and come back and we'll give you extra points type of thing. When I first started, there was no food offered for students. So students had to go all the way to Bryce Jordan Center, which is a little off campus, and then leave Bryce Jordan Center, get lunch, and then come back. And it was wasted several hours. So I increased the amount of money I charge companies, and then started offering food and breakfast to entice students to come. But we really don't have issues with students showing up. In fact, networking and developing those professional connections is such a core component of our curriculum. Like it's in our DNA. That's what we stand for. Our alumni love us. We're a very tight community. My alumni come and give scholarships all the time. I've been very successful with fundraising just because they believe in the education they received, and then they come and recruit. So it's a very tight community. That's niche community, but very tight and very supportive. So from day one, as soon as students show up, we keep emphasizing. In fact, we use it as a recruitment tool. Like, you need to know our community. You need to make those connections, because a Penn State degree, yeah, you're becoming an engineer. That's great, but perhaps even as valuable is that you're becoming an engineer with an incredible network and a Penn State infrastructure behind you. So that never really had a lot of issues with students showing up, but we did a few other things to entice them to stay the whole time and talk to as many companies as possible.
Yeah, it's great. And finally, where do you see the opportunities when it comes to research, construction management, and architectural engineering collaboration?
Sure. So because construction is already part of our department, so it's like integral, right? There's a lot of construction and energy efficiency interface. So many of my construction faculty are also my energy efficiency faculty. And then my mechanical faculty and construction faculty are like this. So that's one area. And then some of my structural faculty and construction faculty are intertwined. In fact, this past year, one of my faculty that was like earmarked for the structural option area said that he doesn't see himself as a structural. He thinks he's more of a construction person, but he's materials, right? Because he said he's more of a construction materials type person. He changed options, and it's really tightly combined in terms of materials area, new construction materials, new construction techniques, and working with structural engineers to redesign the way structural systems are put together such that they're more amenable for fabrication, they're more amenable for manufactured construction, robotics and automation processes. So that's definitely an area of interest. We put a lot of emphasis on in situ construction, like robots navigating the construction sites and debris, and being able to determine what piece to pick and where to put. So deploying robots on a construction site is definitely a problem. It's still an open research question, and we're actively working on it. I encourage everyone in the room to think about that as well. And data. I hired a number of faculty members with focus on computer science, and they're machine learning experts. And data visualization is a key aspect in many of the construction applications to find like improved process design. Oh, I should mention this. We have an operations research doctoral degree at Penn State in College of Engineering, and many of my construction doctoral students actually do a dual PhD with operations research. So like they gain these optimization and modeling and process design experiences through industrial engineering as well. And I think that's a nice synergy to consider. And lastly, this is more educational. Is it okay if I tell you some of the ideas we're exploring for education as well?
Sure, because there is an interest from the audience. One of my students asked a question about the way getting into master's and PhD in your program, but just I think that could be a start point if you
sure. Okay, I'll just do a little example of how we are constantly innovating our education and customer experiences. So here's what we discovered. In a given semester, in the beginning of a semester, a faculty member gives a semester-long project assignment. And then students throughout the semester submit interim reports or interim updates or progress. And then by the end of the semester, they complete the project and turn it in. But real life isn't like that, right? In real life, there are curveballs, constraints change and requirements change, the budget changes. And as an engineer or a construction manager, you need to be quick on your feet and adjust. So we are actually now intentionally introducing curveballs in our classes, and that gets students a bit nervous, but I mean, we're asked to experience and practice those skills of thinking about the future changes that may come your way and make robust designs. So we're introducing robustness to uncertainty or robustness to hard to control factors into our curriculum. I'm so excited about that. Oh, about our master's and PhD programs, if you're interested, just send me an email. My name, SEZ, is my email. So it's sez@psu.edu. There's only one Sez at Penn State, or you can just go to our website and my picture is plastered everywhere. So just click on it and then send me an email. I'll get you connected with our graduate program officer and staff member. We have individuals who run our graduate programs, and I'll get you connected with the right people.
Specifically the question from a student asking about the ways, I think, interested about what are the options for being supported economically? Masters and PhDs.
Right. So our faculty members, we have tremendous amount of research projects. We get funded from Department of Energy and National Science Foundation. So I'll give you a couple examples. One of my faculty, Hutan Jebeli, just got 4 projects this past month. Becca Napolitano has 4 projects within her first year as an assistant professor. Yu Ching, who has 4 projects. Nathan Brown has 4 NSF projects. So my faculty have a lot of funding and a lot of research projects that they're always looking for exceptional graduate students. So if you're interested in graduate research assistantship, there's always a need. And then we also have what we call graduate teaching assistantship, and those are for grading assignments. So you essentially help a faculty teach a course, and those are funded from my accounts from the department, and we have about 26 of those, and we're ramping up to 37 in the coming years. So we're always looking for teaching assistants as well. The way to go about that is obviously, someone with a construction background will be a good fit because you've already taken construction undergrad courses, you will be a good grader. And if we are actually recruiting domestically within the United States, it fits better because sometimes language barrier becomes a little bit of a student coming from abroad, we try not to give them a TA assistantship first year just to help them get acclimated and maybe leave it to a second year. But a domestic student will be a student from the United States, somebody who received their undergraduate from the United States will be a good fit because you've already taken the courses in English language. So I will definitely encourage everybody to pursue that. We also have fellowships. And these fellowships are either funded through Department of Education or through the endowments that I was able to secure. Some of them are in our department, some of them are at the university level. And the fellowship basically says, wow, you're exceptional, we're going to give you some money, do whatever you want. But to be able to get a fellowship, you need to have a faculty watching for you. So let's say a faculty member says, I really like this student, I want to work with him or her, nominates you to a fellowship. If you get that fellowship, then your advisor and you can decide what area you're going to work on. And those are up to 5 years. Excellent.
Thank you very much. We really enjoyed our conversation and your talk. I hope in the future we'll see you here in person as well for another presentation.
Fantastic. Thank you so much. And Stuart, we'll invite you back so that you get to.
We were disconnected.
Oh,
I'm disconnected. I could not hear you, Sez.
Oh, I think we froze. One of us froze. I was saying thank you for the invitation, and it was wonderful to meet you.
Thank you so much. Hope to see you in the future. Bye-bye.